Welcome to our next in a series of podcasts on the Catholic intellectual tradition. Today our guests are Dr. Jason Graham from the Mathematics Department of the University of Scranton and Dr. Duane Armitage of the Philosophy Department of the University of Scranton. So welcome.
Hello, thank you.
So Jason, could you tell us about your background, your educational background?
Sure, yeah. So I obviously went to elementary school and high school and then eventually college. When I first went to university, I was interested in physics. Before going to college, I got interested in relativity in particular. So this is what I want to study. And pretty soon, I learned that I was actually more attracted to mathematics. When you start to study physics as a sort of an adult, you realize that all the equations that you had to sort of memorize in high school are actually solutions to differential equations. And then in math, you show that you can prove general theorems about differential equations and that add additional power to the statements that you are interested in physics. So that's what attracted me to math, and in particular applied mathematics.
So then you got your undergraduate degree where?
I got my undergraduate degree at the University of Houston, and then I started graduate school at SMU and then moved with a faculty member from SMU to the University of Iowa, where I completed my PhD.
Okay, Duane, could you tell us about your educational background?
Sure. I was just on the podcast yesterday, or 2 days ago. I did an undergraduate at the University of Scranton, and then a master's degree at Boston College and a PhD at the New School. My research interests are postmodern philosophy, German philosophy, and phenomenology. And phenomenology began with Edmund Husserl, who was a mathematician, and his first book, The Logical Investigations, were pretty much an investigation into the nature of mathematics, or the nature of intelligible realities. And he concluded with a kind of strange Platonism of sorts. And so I got interested in philosophy of mathematics sort of a roundabout way, through postmodernism and then through Husserl, and then through just questions on science and things like that.
All right, so our topic today is on the philosophy of mathematics. It seems to me that the central question of the philosophy of mathematics is whether or not mathematics is something that's discovered or whether it's created. So whether it exists without regard to the natural world or to the person thinking of it, or is it just some construct that we have in our mind that is not universal? So Jason, do you have any thoughts?
Yeah, so I tell a joke a lot that when people ask me the difference between pure mathematics and applied mathematics, I say, well, I don't really know the difference, but I can tell you the difference between a pure mathematician and an applied mathematician. To a pure mathematician, mathematics is everything. To an applied mathematician, everything is mathematics. So it's certainly appealing to me to think that mathematics is sort of there naturally, independent of human thought, but I have yet to, I guess, form a sort of belief one way or the other.
I will fix that by the end of this podcast. Duane, your first thoughts?
Yeah, so, I'm convinced by Platonism, even crude Platonism. There's a lot of different versions of Platonism, but I believe, I think there's pretty good evidence to suggest that mathematical objects are real, that they have some kind of ontological status. Now, what that is different than the way this table has ontological status, but I think they're mind-independent realities. And I could maybe say a little about why, or maybe we could talk about too.
Yeah, I think actually if you could explain a little bit more about what that sort of means.
Okay, so maybe we should back up a little bit and say, what are the general theories about the various opinions on philosophy of math? And there's a lot, and you can't name them all because then there's subdivisions of these. As far as I understand it, and correct me if I'm wrong, because I'm a philosopher who studies this stuff, but when I read the mathematics, it's never really sinking in like someone who knows the field better, and so I'll understand it for a day and then forget it because it's just too complex. And so I think I get it and I think I understand it, but the mathematics is very difficult for someone who's not a mathematician. about a philosopher of math or a philosopher of, intelligibility or something like that. So I see it, there's obviously Platonism, which is maybe the oldest, the idea that, began with Pythagoreans even before Plato, that objects were real and they would worship them and stuff, and that there was some kind of mystical experience you can get by doing math, And I always say, because I agree with this, I always say the mathematicians are the metaphysicians. The real metaphysicians are on the third floor of LSE. They're doing metaphysics, i.e. metaphysica, going beyond the physical. So there's Platonism, which mathematical objects exist in some way, whether in a Platonic world or whatever. Opposite view of that would be something like mathematics is just a form of logic or reducible to the rules of logic, which is called logicism. It was popularized by Russell and Whitehead. And then something like formalism, which is usually attached to Hilbert, which is the idea that mathematics is a kind of game that you just sort of set up the rules and you can define. It's kind of playing with symbols, and if you just define all the rules, you'll be able to define it. So it's just a language game of sorts. And then there's something I've been getting into recently, actually by way of Dr. Graham. I think we had a conversation 7 years ago about, you should read up on this. Intuitionism, which traces its legacy to Kant, philosopher Immanuel Kant, which says that mathematical objects are constructs of human subjectivity, and it's really interesting the way it does this. And Kant's philosophy of mathematics is interesting in and of itself, but basically mathematical objects are somehow the construct of a shared human subjectivity. But the problem, I'll stop there. Yeah, but there's a kind of subjective universality to mathematics, or a subjective idealism. Kant called his project transcendental idealism. So mathematics doesn't really exist. Mathematical objects don't exist out there in some Platonic world, but rather they're a shared human construct, I guess would be the best way to describe intuitionism, which is traced to a guy named Brouwer. Forget his first name.
I was just going to say, the only thing that I really sort of remember about the difference between, in particular, formalism and intuitionism is sort of what your feelings are about transfinite induction, and in particular the axiom of choice and the use of proofs.
Okay,
Well, in formalism too, he rejects a proof by contradiction, because if you're going to assume a proof by contradiction, then you assume a statement is either true or false. Where he's saying that just because it cannot be true, or just because it cannot be false, does not make it true.
Sorry, that's formalism or intuition?
Intuitionism.
I think you said.
Oh, sorry.
Yeah, that's what I think.
Intuitionism.
Yeah.
That's intuitionism.
Yes.
But formalism they allowed. But in formalism, he's not giving the objects any kind of meaning. It's a board game. We look at the back of whatever we make up, whatever we want on the back of this table.
Yeah.
And then we play the game.
Yeah. Okay.
I think Hilbert's famous statement was you have to be able to replace points, lines, and planes with chairs, tables, and beer mugs.
Yeah.
And everything should still work the same.
Yeah.
It's a very German statement.
Okay.
Right?
Well, let's make this first distinction. I would put Platonism on one side, and then the other three, and various subdivisions of those on the other side. Namely, the idea that mathematics is real versus mathematics is constructed in some way.
I have a question. I'm still maybe a little bit confused. Is Platonism a philosophy of mathematics, or a philosophy that has something to say about mathematics?
Both. There's obviously the philosophy of Platonism, and then there are various philosophies of mathematics that call themselves Platonism with an asterisk. There's, I forget the different versions, but there's something like crude Platonism, which if someone's a crude Platonist, there's something like they accept exactly the way Plato thinks, that there is a realm with where 2 is floating in non-space and time or something like that. I'm actually closer to that. Then there's something like, there's qualified versions of Platonism, I forget all the names, but basic, I don't see really a distinction between all of them, because if you grant ontological status to numbers, that's fine for me. How they exist is not really, that's a different question as to whether they actually exist or not. And to return, by the way, to the point you brought up about intuitionism, it does reject, in logic, the law of excluded middle. It says that, that something either is or it isn't. In this case, it would be a mathematical proposition is either true or false. So Brouwer was famous for rejecting that. And I would say intuitionism reduces, and this is something interesting to maybe, and this is the connection with Kant. Intuitionism, as Kant did, reduces mathematical truth to provability or to constructability. So that's why you don't really know whether something's true until you really worked it out and sort of proven it. So this sort of, you get into all kind of problems with this as well. But yeah.
So Brouwer certainly excluded the use of the middle. However, I've never in my entire life seen a mathematician who is unafraid to use the proof by contradiction in his work. Right, so it hasn't impacted the way mathematicians think about their work. No one is going to read a paper and say, I disagree with this because they used a proof by contradiction.
Right, yeah.
Nowhere ever.
Absolutely.
To my mind, I think, as Duane said, the two schools of thought are whether you have the Platonism or you have something else. And in Platonism, you have the idea that mathematics exists even if the physical universe doesn't exist, and that the statements are true and they're always true, and that even if there was no human beings, mathematics would still exist in its complete and total form. The other ones want to say that it's not, but they give various reasons for why it works, right? Because the fundamental question that it comes down to is, if it is something we construct, why does the world have to obey mathematics?
I was just going to say the same thing, and another way of asking that question. So that's the question of the applicability of mathematics to the world. Then there's the question of, which is analogous to this, and even I think the same question, just asked in a different vein, so to speak. Why is it when you do an equation and a proof, and you do this, why are you going to come up with the same answers, or why when he proves something will you go, oh yeah, okay, that works? In other words, why the move from this particular empirical working out of it to the universality and necessity of it? Now, Kant's answer to that was, well, this doesn't really make sense to us. Now, space and time, the way we understand them they're a priori forms of subjective intuition. That is, you share the same a priori sense of subjective intuition, so when you do something, when you work a proof out, I assume I have the same cognitive faculties and a priori sensibilities, and so we work it out. Now, the problem with Kant's theory there is that we, with different geometries and things like this, different notions of space, Kant was really working with just a Euclidean understanding of space and time. It gets more complicated, and you have to sort of reject that. Never mind the question of transfinite numbers and all that kind of stuff, which is really, that's when it gets sort of hazy for me, but I get the idea. This is the Cantor stuff, and so moving around this, so there's that problem, which Gödel apparently. Go please.
I just want to make sure. So there are two different things though. There's cardinal numbers and ordinal numbers, and Cantor kind of did both. And I think it was his theory of ordinal numbers that was initially met with some skepticism by the larger mathematical community at the time.
Well, the ordinal numbers are extremely interesting, I think. But it's very difficult to have an intuition about the ordinal numbers unless you work with them for a long time. For example, you could take the smallest ordinal number, which we call omega. We use the small omega to indicate this. So if you might say, okay, here's the ordinal number omega. What is 1 plus omega? Well, 1 plus omega is omega, because that makes sense to you, because you say the infinity sort of absorbs that 1. However, omega plus 1 is not omega. It's omega plus 1. It's like the game school children will play, where I say you stink and you say I stink, and then I say you stink infinity and you say infinity plus 1. Right? That infinity plus 1 actually has a meaning as an ordinal, not as a cardinal. As a cardinal number, it's the same. But as an ordinal number, it's something more. So 1 plus omega does not equal omega plus 1, which seems very odd for your intuition. But omega plus 1 is you go to infinity, and then you go a step beyond. So in the ordinals, you'd have omega plus omega is then different than omega.
Yeah, that's very non-intuitive to me.
One thing I'd like to point out, especially as an applied mathematician, is a lot of this work was actually inspired by mathematicians of the time trying to understand in detail and rigor, at an appropriate level of rigor, Fourier's theories and Fourier analysis that came out of Fourier's attempt to try to understand heat.
Oh, okay, I didn't know that. That's interesting. I have a quote by Gödel I wanted to read just in this context. I thought it was. I found two quotes from, and so I don't know if maybe this doesn't apply, but he's talking about the negative attitude toward Cantor's set theory and about the relationship because of the way it considered mathematical intuition. So he says, and this is Gödel. I forget what the paper is called. It's in the footnote here. The negative attitude toward Cantor's set theory is only the result of a certain philosophical conception of the nature of mathematics, which admits mathematical objects only to the extent to which they are interpretable as our own constructions, or at least can be completely given in mathematical intuition. For someone who considers mathematical objects to exist independently of our constructions and of our having an intuition of them individually, there exists, I believe, that's Gödel, a satisfactory foundation of Cantor's set theory in its whole original extent and meaning, namely axiomatics of set theory interpreted in the ways sketched, and he's talking about Platonism there. So Gödel was a very serious Platonist. So I think, but he, but apparently he had some interest in trying to synthesize the insights of Brouwer with, what he was trying to do. But
Well, so let's explain a little bit about what this set theory means. So in the late 19th century, early 20th century, they tried to formalize mathematics. So in other words, mathematics was a collection of things people had done, but they wanted to really isolate the things that we were assuming. And one of the attempt that stayed was the Zermelo-Fraenkel set theory. And so this was the basis of all of mathematics. We would assume some very basic things, like that there's a set with no elements and things like this, things that are so incredibly elementary that no one would question the ability to do this. In other words, these are rules of the game that everyone would allow. But when Cantor comes along, he allows another thing, which is called the axiom of choice, which was found because people were proving things, but then somebody noticed they were using an axiom that was not part of the Zermelo-Fraenkel axiom set. And basically what the axiom of choice says is if you have a collection of sets, then you could have a function on that collection of sets that picks an element out of each one. It sounds absolutely obvious, right? So people were willing to accept it. However, the consequences of the axiom of choice are incredibly unintuitive. Mm-hmm. So while we said no one ever writes a paper and says, I'm sorry I used the law of excluded middle, ever. I've never heard that happening. Papers in topology, in set theory, will say, put an asterisk by this, like a steroid-induced home run. I proved this, but I used the axiom of choice. So while most mathematicians, I think, accept the axiom of choice, we're still a little bit hesitant to work with it.
is it because of the non-intuitive results or something else?
Well, here's one result. Say you have a ball.
Yeah.
So a ball is not a sphere, it's a sphere that's filled in.
Yeah.
You have a ball of radius 1. If you accept the axiom of choice, which seems absolutely obvious, then you could take the ball of radius 1, cut it up into pieces, reassemble the pieces so that you have 2 balls of radius 1.
Yeah.
Which is completely and totally unintuitive.
Right.
Which is called the Banach-Tarski paradox.
Right.
So if somebody says, accepting the axiom of choice as an axiom is the same exact thing as accepting the Banach-Tarski paradox as an axiom. So you were happy to accept the axiom of choice, but I don't think anybody would be happy to say, okay, this is an axiom because this is absolutely obviously true.
Right.
Right? There are other things that are maybe harder to understand, like the well-ordering principle and things like this, which has a major effect on the cardinal numbers, for example, if all cardinal numbers are well-ordered or if they're not. If you don't assume the axiom of choice and you have non-well-ordered cardinals, the theory becomes extremely difficult, much more difficult. So, I mean, the question, some people might say, well, okay, there's 2 mathematics. There's one where the axiom of choice is true and one where the axiom of choice is false. So you could still, if you accept that, you could still have a Platonic view of mathematics. It's just that mathematics is the big thing that contains these 2 independent mathematics inside it. One where the axiom of choice is true and one where the axiom of choice is false. But where I think it gets different is, say, you take the continuum hypothesis. So the continuum hypothesis is about cardinals. So the continuum hypothesis would say there's no set whose cardinality is bigger than the cardinality of the integers, but smaller than the cardinality of the real numbers. That also is independent of Zermelo-Fraenkel set theory. But it's harder to accept a mathematics where this is true and one where it's false, because you're really talking about a set of the real numbers. Because if it was false, there would be a set in the real numbers, right? Some subset of the real numbers whose cardinality was different than the real numbers and the integers. It's hard to believe that that could be false or true. So a Platonist, I mean, what Gödel would say is, no, this is either true or false. We simply do not have the ability to prove it. Mm-hmm. So it's knowledge that's, so if you look at Gödel's idea is, okay, this is true or false, we cannot prove it, but it's still either true or false. That's in mathematics, because this set either exists or it doesn't exist. Right? So you can't, if you're looking at the way Gödel would talk about things, right? You can't just say, okay, we're going to do this. But you could see all kinds of papers written in set theory where they say, well, if the continuum hypothesis is true, then this is true. If the continuum hypothesis is false, then this is true. Because if we can't prove it, we still want to write papers, so we're going to say, explore what's true on either side of this.
Yeah, it does. I mean, from a sort of practicing mathematician standpoint, it's what type of pathologies do you have to allow? In other words, you define some mathematical object, and you have to decide how far am I willing to go with regard to what type of objects am I going to allow to fit this definition. And when you accept or do not accept these kind of ideas, that's what you have to work with.
Mm-hmm.
But then you can always, make stronger hypotheses so that you can rule out having to worry about these sort of things.
But even, it seems like someone might be listening and saying, well, this has nothing to do with the actual application of mathematics in the real world. But it does. Throughout time, there have been questions that have arisen like this. Say about even the real numbers, the construction of the real numbers. You're really assuming lots of things about infinity along the way, right? So the whole world is not just based on finite mathematics. So these questions can actually come up in the applications. But it seems, as we said, the perfect example is the Higgs boson. Higgs proved the existence of this thing with the mathematics. He said the mathematics says that this must exist, so it must exist. And many people didn't believe him. It was 50 years later that they actually found this experimentally, right? But the idea was, if mathematics says it's so, it has to be so in the natural world.
Yeah, so this goes back to, this is why I'm committed to a kind of Platonism. It just, I wouldn't be able to understand why mathematics is not only applicable, because it seems like if it's applicable, it has to be catching something in the world, right? It has to be catching something. And why, and by the way, when you say mathematical objects, or mathematical objects are real, and Platonism is the idea that they are real, it doesn't mean that the language is the way it is. It means that the language refers to some object, I guess. And so it just seems, I don't quite know how to understand that. I have, otherwise, because so much of science is all of science really is contingent on mathematics. It just seems like, what do we do? Now, there are theories in science, which is in philosophy of science, that says, like, for example, a radical theory would be something like Nietzsche, or just in general, instrumentalism, it's called. The idea that, look, all mathematics and all human science is construct. It just deals in paradigms and models. The models predict somehow they're working, but they tell us absolutely nothing about reality, and we'll have a paradigm that probably will contradict the next one, and we'll be able to work with it. And it's just somehow human beings are able to dominate and control nature by, like Nietzsche gives the example of the intellect is like Procrustes' bed. It stretches and crushes it until it fits in. Yeah.
It seems like they're axiomatizing their desired end.
Yeah,
and then seeing the world through that form.
Yeah, I think a lot, I don't know, for me at least, a lot of these conversations are thrice removed from the deeper philosophical questions that, like, is there a God, or is mind more fundamental than matter? Like, because you're into a problem, and Nietzsche saw this, by the way. If mathematical objects are real, then you're dealing with, kind of spiritual, spooky kind of things out there. Like, what does that mean? Like, that you're letting something in the back door that, a strict empiricist would be very uncomfortable with, I think. Yeah.
So let me ask this question then, since you brought this up. Does a belief in God imply a Platonist view of mathematics? And does a Platonist view of mathematics imply a belief in God?
Not necessarily, but I think so.
Which way?
I don't think belief in God implies a Platonist view of mathematics. There are people in philosophy of mathematics who believe in God that aren't committed to any particular view on mathematics because that really has to do with their theology, though. Like, what is God then? Because you run into problems then, like Plato ran into, or like Euthyphro, the Euthyphro dilemma, which is with regard to morality. Like, does God create the numbers, and are the numbers eternal with God, or is he somehow subject to those, or did he create them, or so it has to do with this idea of divine.
So, but if God is omniscient, if you took a Judeo-Christian view of God, and you say God is omniscient, then doesn't he know the results? He knows if the continuum hypothesis is true or false.
Yeah, but if
so, does that mean that that it has to be a Platonic view of this? If God knows whether the continuum hypothesis is true or false, we could, he used it to make pronunciations about mathematics.
Yeah.
But if you could actually talk to God and say, hey, what's the deal? He could tell you the answer. So that would mean that there was an answer, truth beyond that.
Absolutely, yeah. But the problem is, like, what are those truths somehow alongside of God, or are they a part of his essence, or something like that, or is he subject to them? Are there co-eternals with God? Now, the ancients just said, well, the logos, this ordered principle, all the intelligible realities are somehow reflective of the mind of God, like sort of going through a prism, and then the light sort of disperses, things like that. Yeah,
I would say they were part of God's nature.
yeah, exactly.
In the same way, God can't be illogical, right? God can't do evil. God can't do all these things. Like, the old philosophical question: could God make a rock so heavy that God can't lift it? Right? God can't act against His nature any more than anybody else can. So I mean, He can't. Mathematics is not. He's not subject to mathematics so much as it's part of His nature.
Yeah.
Right?
Yeah.
In my view.
I agree. I think that way. So I'm much more familiar with logic, and when logic gets sort of mathematical, that's what I understand. That stuff seems to me like when you start getting into that seems real, and I think there's no problem with calling the logic the logos, somehow reflective of some kind of larger reality. I think. Yeah.
So Jason, your thoughts?
I don't know. I mean, this is one thing that you brought up that I am particularly interested in, because I do a lot of mathematical modeling. Is this sort of our models, real-world models? I can say some more about that, and then I'll maybe.
Yeah, there's a guy named Larry Loudon. I think in the '60s or '70s, he compiled a bunch of scientific theories that were completely false but worked.
Yes, yeah.
And had real predictive value. So we were talking about Ptolemaic navigation the other day. Like you can sort of squeeze those ones in, but some, or even like something like Newton and Einstein, where you can make them what Thomas Kuhn called commensurable. You can make the paradigms commensurable, even though they're kind of not. But there are some theories, and some things in chemistry. I forget. Some of them are escaping me now, but they're completely false, and they have predictive value. And so the question becomes, and I think you are justified.
I would argue that false is not the right word. I would say maybe it's a spectrum of accuracy.
Fair.
More than a binary true-false.
Yeah,
I agree with that completely. Because if you take that view, as we talked in our last podcast, if you take the view that the Earth is the center and the sun goes around the Earth, that's clearly the wrong paradigm. But they were unbelievably accurate at predicting everything. They could tell you where the sun was coming up. They could predict all the astronomical events, and they could navigate by it. So it wasn't that the model was wrong, because it is right. If you think of one thing going around another, right? This seems like an exercise you'd give in a graduate class. You say, okay, right, B is going around A. Now assume that A is going around B, that's the action, and now redo all the rules. It would be 1,000 times harder to get it right, but it's still a model. It's just not a good model.
Yeah.
Right, because the physics is saying the Earth goes around the sun because of certain reasons, because of the reasons of gravity.
Yeah.
Right, but if you want to take a mathematical model that's completely predictive, you could take the old model, which is why they were hesitant to give it up, because they said, look, it works.
Yeah.
Right, so
Yeah.
there are lots of models like this where you say, you might get incredibly complicated a system of mathematical results, and say, look, this is predictive, but it might be, in quotes, the wrong model, because you could get a much better model that's better in predicting what's going to occur.
Yeah.
Right. So the modeling of mathematics is it's not necessarily a Platonic idea. Right. This is If I can make the philosophical statement, I think of it as because you were bringing this up before about the language we use in mathematics. I think of it as Plato's allegory of the cave. Right. So you have the light, and then you see the shadows on the wall. So the modeling is trying to use the shadows on the wall to figure out what's going on.
Yeah.
But the sun out there, Plato's sun, still exists. So the mathematics is still perfect and pure, but how we apply it is not always perfect and pure.
I think, and I think you could have a kind of Platonism of approximation, or say that our models and our whatever can approximate. But that's one thing. To say that we're just shooting from the hip and getting it right somehow without these things being real seems to me, I just don't. So why I'm a Platonist, I just can't understand what that would look like if mathematics and science is so successful, if it's just not mirroring something. And then again, back to that question of the universality and necessity of mathematical proofs and things like that. Like, why are they universally communicable, and why are they necessarily true? Like, this is a very strange thing to me.
But I think you could look at Newtonian mechanics in that way. If we're building a house and building a car, all we need is Newtonian mechanics.
Yes, yeah.
Because we're not building a car that's 3 times the size of the sun, or a house that's going 0.9 the speed of light, right? So it's not that the Newtonian mechanics are wrong. It just doesn't. If you look at the actual equations of what's going on, there are things that are so irrelevant when the objects are slow and small, that it doesn't make the slightest bit of difference, so that we could still build a car, we could build a table, we could build a house using Newtonian mechanics at all. It's not that it's wrong, it's just that it's not encountering every single thing. In the same way, to say the efficacy of mathematics, there was also Einstein predicted the gravity well, right, in the orbit of Mercury, right, which it was just purely mathematical, because before, when they looked at the model, they looked at the where the orbit was going, they just thought they made a mistake in the observation, but they didn't. It wasn't a mistake in the observation, it was really true. But Einstein predicted it simply through the power of mathematics, not by observation. So why is it obeying this incredibly difficult mathematics that's just reasoned out on a sheet of paper? Right?
Yeah. It's somehow relevant to this question that we're sort of kicking around here is Heisenberg wrote a book on philosophy. It's called Philosophy and Physics, and in there because he's dealing with quantum mechanics and some of the paradoxes you get into, because then you have to take into account the human subject when it's trying to measure stuff, and then and so it's sort of what you're getting at with the Ptolemaic thing, and when, from a perspective, and then the perspective gets larger or smaller depending on what you're looking for. Heisenberg's conclusion of that book, which isn't very promising, it's that our language we have mathematics that goes beyond language, and our language can't translate back into something intelligible, which then, that's interesting when it comes to, back to our initial discussion we had regarding intuition, and why we might get paradoxes in intuition and things like that. So, I don't know, I just want to throw that out there because it just made,
This is slightly off topic, but something that each of you said reminded me of this. I was just reading the difference between Heisenberg's approach to quantum mechanics, the so-called matrix mechanics, and Schrodinger's approach via what's now called the Schrodinger wave equation. That Heisenberg was essentially fitting the model to data, and Schrodinger was not really working with data at all. Yet, after significant efforts, it turns out that these two mathematical theories are equivalent, but coming from completely different directions.
Yeah, there's those little books. They're sometimes better than the bigger books. Like a very short introduction. The quantum mechanics one is actually pretty good because it lays out the various 6 or whatever interpretations of quantum mechanics. And I've heard there are people there's a guy Sean Carroll. Where's he at? Caltech.
Yeah, I saw him talk once at the Secret Science Club in Brooklyn.
And that's pretty cool. He's the many worlds theory of quantum mechanics. So he thinks there are infinitely many. If it can be, it is somewhere. So when you look at something and it splits, there are all these worlds and things like this. Which
he wrote a super nice book on relativity.
He did.
Yeah.
That's it. Yeah.
Like a textbook.
Yeah. Cool.
I think in terms of quantum mechanics, the quote I like the best is the person who says, when someone tells you they understand quantum mechanics, that means for sure that they do not understand quantum mechanics.
Yeah.
Right?
Yeah.
But I mean, quantum mechanics, I think, is the perfect example of what we're saying. It's very hard to get empirical results. It's almost impossible to have an intuition. So we're in the dark with a blindfold on. All we're doing is using the mathematics as our guide. The mathematics is our one and only guide into this world because we simply don't have empirical evidence or intuition.
There is a recent book actually about this. What is it called? I don't remember now. But basically, it's by a particle physicist who's kind of critiquing the current approach to scientific investigation and particle physics. It's like How Beauty Led Us Astray or something like this. I forget the exact
I saw
title.
that. Yeah.
But it was pretty interesting. I wish I could say more about it. I'm not a physicist, but I mean, it's kind of this idea of how far can you go from the data and still be doing good science, and how much should you rely on sort of a particular idea of mathematical beauty to guide the scientific investigation. And so this author argues that we've gone too far in the direction of the beauty of math, because now we're not really producing results anymore. We're just...
I know Penrose. I think Penrose has a book on this, among his many books, on beauty in mathematics, and how when mathematicians or scientists will get stuck, they'll go more with the aesthetically pleasing version. But he, by the way, is a Platonist.
Well, I think in mathematics...
No, go ahead, yeah.
In mathematics, there was a mathematician named Erdős. And so Erdős had a belief in the book. And the book, as he called it, the book, was a book that, say, exists in heaven, where the correct proof of all the results lies. So it's a proof that is aesthetically pleasing. It's the highest level of aesthetically pleasing. And Erdős would always say, you don't necessarily have to believe in God, but you have to believe in the book. So he was really looking at this as very Platonic view, that there was a perfect way to do mathematics. So when someone would write a really good proof, the highest praise you could get from Erdős was, that's a proof straight from the book. So he was opting for the aesthetically pleasing, right? So basically he would say, okay, yeah, you could prove this and you have it, but it's not from the book. That's not the right way.
Yeah.
But it is a way. But you're not getting to the real heart of it.
Well, Kant Kant has something, he says there's something very similar, which, by the way, I find that appealing. I think there is a book up there that we could just read off one day. But Kant has this idea in the third critique that the principle of science or scientific investigation, which I presume includes mathematics, is that we act as if the world was ordered by an understanding, he says. Now, of course, you can't prove that, but that's just the regulative principle that has to be sort of in the background that guides, that you have to assume that you have to assume that you're going to discover something. You can't assume that you're putting it there, even if Kant thought we were putting it there. Well, he was a skeptic about it, really. But you have to assume it's there, and that you didn't put it there, even though you're putting it there, you know?
So let me ask a question to Jason then. Since you're an applied mathematician by trade, are all mathematicians closet Platonists? Do we all pretend that it's like there's no atheist in a foxhole, right? So if you're proving theorems, are you really a closet Platonist? Even if it's not what you believe, you have to pretend that you are to do the kinds of things we're doing.
Yeah, that's a good question. I mean, I don't know. I don't know what all mathematicians think, but
Are you a closet Platonist when you're doing
I certainly hope that what I'm doing is real. And actually saying something about the world and not just, being led astray, I guess, by something that I just find mentally attractive.
So you're a closet Platonist is what you're saying. I mean, if when people talk, I know mathematicians who are not Platonists, but when people talk to them, they come away with the idea that these people are Platonists. Because all mathematicians sound like Platonists when they're describing mathematics, even if they are 100% opposed to Platonism as a philosophy of mathematics. Yeah. The way we present ourselves to the world is as Platonists, I think. Right? Because there's a certain arrogance that comes with mathematics that we think, Gauss said this, that mathematics is the queen of the sciences, and then number theory, which I happen to do, is the queen of mathematics. So I'm at the top of the top. But we definitely have this view that every other discipline is completely and totally dependent upon us.
Mm-hmm, mm-hmm. That's true.
Right. But in some sense, we might be the least useful, but everybody else is dependent upon us.
Yeah, wouldn't that be interesting if mathematics is just making it up? Notice I said we're, like I'm a mathematician now, because I'm in part of this conversation for a half hour. But if mathematics, everything's dependent on mathematics, and mathematics is just cooking it up, then what does that say for the foundations of everything else? This is a Husserlian problem, why you got interested in phenomenology. Anyway.
Well, sure, if you look at, the famous cartoon where it's, the biologist is standing there and the chemist says biology is just applied chemistry and chemistry is just applied physics and physics is just applied mathematics. It's all completely true. So if our foundation crumbles, the foundation of physics and chemistry and biology all have to crumble, right? But we know, when you take an antibiotic, you're giving your belief that this is going to cure this infection, right? Mm. You believe what the biologists are telling you about bacteria and everything else. When the doctor goes in and gives you, is going to do surgery on your gallbladder, you trust that what they're doing is right? So we believe in chemistry, we believe in biology, we believe in physics, right? You get in an airplane, you're confident that the airplane is going to take, well, not you, Duane, but other people are confident the plane is going to fly, right? Because we believe in the physics, right? We believe that the people who said this, but all of their work is dependent upon our work. Yeah. Right. So I think if you're not going to take a Platonic view, you have to just say that it's working for some other reason, right?
Well, I want to add to this because it's interesting when you think of. I want to go back to this question of the relationship, and maybe you both have something to say about this. The relationship between mathematics and logic, and how much mathematics is dependent on logic. Because as a philosopher, when people try to critique logic, you get into much deeper problems than if you're trying to say mathematics, because then you can't even predicate anything. Like if there are philosophers, postmodern philosophers, for example, will say, no, logical rules are constructs. And then the question is, well, what allows us to get beyond the construct? Or can we ever get beyond the construct without using the construct? And if the construct isn't real, how do we critique it? So, or just a wholesale sort of critique of reason itself. How do you critique reason without using it? And then Nietzsche did this, and he said, my philosophy is irrational. And then so it's much easier to see the problem with going all the way down to logic. So my question then is logic more fundamental than mathematics, or as fundamental, or is one contingent upon the other?
I would say logic is a part of mathematics.
Okay.
Yeah, that's my position now.
Okay.
Well, I think
Okay.
that the Gödel's refutation of logicism, say, I think that shows that, because mathematics is not, what Gödel's results show is that mathematics is not simply the application of logic, right? You could use, like Russell and Whitehead wanted to say, they wanted to say, okay, we could just use logical rules alone to prove 1 + 1 = 2. And then Gödel said, yeah, but there are results in number theory, statements that are true in number theory that you cannot prove this way,
Yeah.
right? So that mathematics is bigger than logic, but logic is intrinsic to mathematics,
Yeah.
right? And I would say, I mean, to me, the rules of logic can't be a construct, because you take, here's an example. You take a computer. A computer is nothing more than an electrical application of the rules of logic.
That's
It's
cool.
the exact same thing. All it is the rules of logic. So when the mathematicians knew how to build a computer, they just didn't know the engineering, right? So the rules of logic, it's just AND gates, we call them AND gates, OR gates, and NOT gates. All it is the results of actual very elementary logic, not even the complicated logic. Very elementary logic, and it makes the computer work, right? And the computer does work,
That's cool.
right? So, I mean, the computer is like a test of our rules of logic, right? So there has to be something that makes the computer work, because we trust, right? We program a program in a computer, and it works, right? People might say the computer makes mistakes. The computer really never makes mistakes. It's the programmers who make a lot of mistakes. The computer doesn't really make it. It's possible for a computer to make a mistake, but it happens so rarely, and it's simply because something is switched on or off accidentally, right? It's
Yeah.
just it's a part of being in the natural world.
Right.
Right, and you could actually correct for this. And mathematicians who do gigantic proofs on a computer, like Clement Lamb, who proved the non-existence of the projective plane of order 10, he used a Cray for 1 year. He actually had to account for this, and it happened something on a Cray for a year, something like 12 times. I forget the number, but it was small. But he still had to rerun those parts of the program where he knew that this happened. Right, so you really had to be extremely careful.
This is great. I have a couple thoughts here. I just lost it. I know what I was going to say. Well, logicism is interesting because now I don't know Russell's entire. I've read a lot of Russell, but at certain points I know he was a Platonist. I don't know if he refuted that or what. But logicism, trying to reduce mathematics to logic doesn't necessarily rule out Platonism. It just rules out a kind of Platonism, maybe mathematical Platonism or something like that. But Russell, I think, as far as I know, at a certain point, as I believed in the rules of logic, where had Platonic existence, things like that. Now, what else is interesting, back to the Gödel thing, is that at least there's certain people, I'm persuaded by this, but again, I don't know the mathematics as well as you do, so that Gödel's proof has implications. Certainly Gödel thought so, and there are others who agree with this, so I'm not alone here, but Penrose thinks this, that Gödel's proof, if not points, leads directly to a kind of Platonism, because it can't reduce truth to some, provability, or just simply
So it can't reduce it to the mechanical.
to the mechanical, yeah, and even with regard now, so you could see that with regard to formalism, that it's not just a bunch of games, or you just define the rules. But when it comes to intuitionism, it gets more interesting, and that's what I've been interested in lately. Is does Gödel's proof rule out intuitionism as a kind of alternative? And I think there are some who think it does. Now there are people who always will disagree. Okay, there are always people who say no, you can. I'm working on this to try to fit it. But certainly Gödel thought it did, and precisely because if having to do what we talked about, there are mathematical truths that are true that you either can't prove yet, or or just even the idea that this sentence is not provable in the system.
I think it's always in the context of a system.
Yes, yeah. But there are truths in the formals in any system that would have to go beyond that or something.
Yeah, well, there are some restrictions on that, like a system that can.
Rich enough to have Peano's axioms. That's
Yeah.
the big result.
Yeah.
But I mean, Gödel's work has Gödel was partially responsible for proving the independence of the continuum hypothesis, and I think it's the Gödel completeness theorem, which is never talked about, which is in some sense more important. Where Gödel's completeness theorem says if you if you have a set of axioms, then they're consistent if and only if you can construct a model for these axioms. That's how you show the independence of these things, right? So that if you're showing the independence of the continuum hypothesis, you're using Gödel's completeness theorem. That's the more powerful tool. Everybody talks about the incompleteness theorems for their philosophical implications. I think the completeness theorem is the one mathematicians actually use, and it really has a ton of philosophical implications, just people don't understand it. So when you're showing the independence of an axiom there, it's really showing that our intuition is not big enough to get to all of truth.
That's cool.
Truth is so, because basically what he's showing is it doesn't matter how many axioms you add to Zermelo-Fraenkel set theory, we're never going to be there, right? And also we cannot prove the consistency of mathematics when within mathematics. So you have to be outside of mathematics to prove the consistency of mathematics, which simply can't happen, right? So it's just showing that we're really highly incompetent, right? Our intuition is minimal, and so it gets us a lot, but there's just an infinity out there that is we cannot get to. It's ungraspable, right? Which is almost a theological statement, right? So if you posit the notion of a omniscient God, right, then God always knows more than you do, right? No matter what, we cannot get there. There are always theorems that God is going to know that you are not, right? No matter how much our intuition works, no matter how much we're able to get, it's just we're taking eye drops out of an ocean. Right.
So I have a question back to what you were saying and then what you build it on upon about truth extending beyond mechanism or provability or decidability with Gödel. So you said, well, only under certain conditions, but still, so as far as I understand it, that would at least point to, or at least Gödel thought it did, the idea that truth would extend beyond that. So even if it's under certain parameters and circumstances, wouldn't that still point to an existence of truth beyond?
I'm just saying that it's a mathematical statement that requires premises.
Oh, okay, I see. Okay, I think
Some people misunderstand Gödel to say that a system cannot be consistent and complete, but a system can be consistent and complete.
Right. Yeah.
You can take the theory of any model, for instance, is consistent and complete. The theory of well-ordered fields is consistent and complete. But what his theorem said is that if it contains rich enough to contain Peano's axioms, then it's not going to be. So it's not that a system itself cannot be consistent and complete. It can.
Right.
But there are systems that are not consistent and complete.
Right.
It's often misunderstood.
No, I understand.
If I remember, there's isn't the fact that you said about the completeness of the well-ordered fields, that says something about geometry too, right? Isn't that Klein's summative fields Klein proved that Euclidean geometry is consistent or something?
Oh, I imagine so.
And it falls
because
back
if you have a well-ordered field, then you built the geometry in the classic algebraic way. But the non-Euclidean geometries, they were a 19th century discovery, and they kind of threw a wrench in people's philosophy of mathematics, because you took the basic axioms of Euclid and you have that fifth axiom, which could be written in many, many, many different ways. Probably the most well-known way is that if you take a line and a point off a line, there's a unique line through that point parallel to that line. And so what the Euclidean view, so I don't mean the Euclidean, I mean Euclid's view, was that these axioms of geometry had to be absolutely true. And what they found out was you could have the first four axioms true and the fifth one be false and still create a geometry. That was essentially, while it didn't explicitly use Gödel's completeness theorem, that's an example of Gödel's completeness theorem, because they show a model of geometry where the first four axioms are true and the fifth one is false, right? But to me, that doesn't invalidate a Platonic view of mathematics, because all it's saying is the universe we live in may not be governed by Euclidean geometry, which I think physicists to say it's not, right? So to say it doesn't make Euclidean geometry any less true, it just means that there are many geometries. So if you were had your home science experiment and you were going to create a universe, maybe you could create a universe with Euclidean geometry. Maybe you could do it with projective geometry. Maybe you could do it with hyperbolic geometry, right? So it's not that one geometry is truer than the other ones, They're just different models, in the same way that you could have
Yeah.
the axioms of group theory, and you get lots of different groups, right? So you have these axioms of geometry, the first four, and then you can get lots of different geometries, just like you get lots of different groups, lots of different number systems, things like that. There's not a unique geometry. That's all that says, which is very consistent with the rest of mathematics, because nowhere else in mathematics do we say, okay, there's only one system of numbers, there's only one system of groups, there's only one system of anything. We accept a plurality there, so we should accept a plurality of geometries.
In fact, I would say that's like the key lesson of 20th century mathematics is it's not objects in and of themselves that's interesting, but how they sort of lay in relation to other objects.
Yeah, I
Yeah.
agree with that.
That's,
Completely.
Which then, I would ask as a philosopher, what's the ontological status of relation? So if thing, so relation is
I would say it continues to grow.
yeah, but is it real? Two other questions I
From a
have.
mathematical perspective, this is something that continues to be a topic of investigation.
Yeah, well, okay, back to, let me just say one more thing about Gödel and the incompleteness, because he was interested in, this is where I know he got interested in phenomenology, because he was interested in, what is it when you can see, Plato was interested in this too, it's a epistemological question, what is it when we see a truth that we don't sort of exactly prove? When we see something as a kind of self-evident truth or something like that. What does that mean? What's the epistemological move where you can see that this is true even though you can't prove it? So if you have the sentence, the way this gets translated is, G is not provable in the system. That's true, but you can't prove it in the system. And so what is what is that intuitive insight that we have when we go, yeah, that's true, but I can't prove it in this sort of whatever system?
Well, I think if we have a system bigger than that, then we can prove it in that system.
I see.
As long as it's within the gigantic system of mathematics, mathematicians tend to accept anything in that system.
Isn't it part of the result that you can always embed into a bigger system in which you can
Yeah.
That's true.
determine?
But then wouldn't there be then another one that wasn't provable? Yeah, then it would just keep sort of, yeah. Okay, my second question is, so again, to a skeptic who's not really sure, what is a possible metaphysics that could explain mathematics without it having some ontological status? Like, just shoot, I'm just curious.
Explain that non-philosophical.
So, how could, okay, and using the terms you asked earlier about what does Platonism mean, and I gave a very broad, it just means that there's some reality, whatever reality means. Maybe it's non-spatial, non-temporal, maybe we need to, reconsider our understanding of what reality is. But there's no objectivity to mathematics. Let's say that there's no reality to mathematical objects, no ontological status. Ontological just means being, there's no being to it. What could mathematics be then, be in parentheses, if it isn't real? Does that make sense? And why does it work? And why does it seem to be systematic? And why does it have universal necessity? Yeah.
Part of where I'm unsure is not so much in the reality of mathematics is there limits to that reality? Are there some things in mathematics that certainly do correspond to reality?
Yeah.
And then are there other parts that just are like icing on the cake? So
He pointed to me when he said that. He's just 5 results.
Yeah, that's interesting.
I
Yeah.
don't know. I mean, like I don't know if I've never heard of anyone argue about even like how much mathematics do we know? Like, of all possible mathematics, like how much has been discovered? Is it just barely anything at all?
I noticed you said
Or
discovered.
Is there? Well, I mean, there's different ways to take that, though. I don't mean it in the sense of
Platonically.
But anyway,
We'll take it in the platonic
so
way.
yeah, so like.
I think
No one, I don't know, speculates on how much there is to know.
I think you're a Platonist. I think just with eraser in hand or asterisk Platonist or something. Yeah.
He's hedging his bets. He's really a Platonist.
Yeah. What? Just because from a philosophical perspective, what else could it be, or what else would it be, or And okay, maybe just to this question didn't come up yet about the foundations of mathematics. So what's set theory, or I remember I was watching some physicists say this, and I know mathematicians hate when physicists talk about mathematics, but this was the guy who Michio Kaku. He was talking about the nature of mathematics, and he said, "Well, it's just set theory. It is counting and the rules of logic." What do you think about that definition?
Of mathematics?
Yeah. Because that made sense to me, but I know from what we've talked about, Steve, that you would,
Yeah,
it's
I
a
think
little bit more
that's
complicated.
that's overly simplistic,
Yeah.
but there is a germ of truth in that,
Okay.
right? I mean, in essence, mathematics is just set theory. But you could be a very good mathematician, really good, and not know a lick of set theory. Our students graduate without knowing any set theory whatsoever, because there is so much more mathematics they have to learn before they're ready to even approach that.
Yeah, there's actually an exercise in this theory book that I was reading before, and it is like just approach a random mathematician and ask them if they can state the axioms of set theory. Almost no one can
Yeah.
do it.
Wow.
I don't think anyone, I mean, it would be hard to get anyone who
You'd
remembers
probably
them all.
be a specialist if you
Yeah.
could do it.
Wow.
Yeah.
Okay.
I mean, if you gave us 20 minutes, we could probably remember most of them. But then it would take another hour to state them correctly.
Okay.
Because it never, in the day-to-day work of a mathematician, you never require these, ever, except the axiom of choice if you're a certain kind of mathematician. But in my research, I've never had to say, oh, well, this follows some set theory, because we just assume all of those things, right? So it's the underpinning. Like, this is under the hood. We never really need to look at it, right?
But don't you want to look?
You
Don't feel compelled
you want
to
to look, but in some sense, it's going to eat up all your time, right? You have to work several layers above if you want to get any results, because it's like a programming language. We could write everything in assembly, which are really down to the ones and zeros, but you're never going to write a program that you could sell,
Right.
because you're just working at such an elementary level. You're never going to get anything interesting. You have to work on a program that's built on assembly, that's built on that, that's built on that. So like a second generation, third generation, fourth generation. Then you're working here, you could really do things fast. So we're like 4 generations away from set theory, so that you could actually prove something that's of use and of interest.
So just 2 quick comments. One was that this observation that mathematicians work a day can't really name the axioms of set theory is partially motivating current research into a different approach to the foundations of mathematics. It's called the univalent foundations of mathematics.
Ooh.
And there was another comment.
Well, if it comes back, just interrupt me, but I wanted to sort of reach across the table and try to make this make sense to a philosopher and to, Greek philosophy and to questions that concern Plato. And again, I know what I'm going to say. You're going to go, no, not really, because I've tried this before. But, so a big question in Plato, back to Plato, but Plato critiqued his own philosophy, and a big question for him at the end, this is in the later Plato, it's some dialogues like the Parmenides and the Theaetetus, where he questions the nature of the forms, and he gets it, you can't really figure out how they go together in the world, but at least he'll say this, like, we have to assume, he doesn't use the word, we have to use the word axiom, I don't think, in the Greek, which just, by the way, means worthy of assumption or something like that, but he says, the question is, do we assume that something like the logos exists? And what does the logos mean? Well, logos comes from the Greek legein, to collect the hen, or the panta into the hen, the many into the one. And so logos is this collection. It's this activity of collecting. So we just gather things into one. And the question then becomes, are ones real, or are collections real? And so when I hear you talk about set theory, common in the common tongue, or whatever you're doing here, dumbing it down, is that a similar point? We're talking about sets as collections of things. I mean, are collections real? Is reality collectible? You see what I'm saying?
Well, I mean, a set is a necessarily undefined object.
Mm-hmm.
You cannot make a definition of set. That's one of the paradoxes, right? If you try to define a set in terms of logical language, you reach Russell's paradox, and saying, no, you can't define all these sets like this. So the fundamental belief of this is that we can collect objects in sets. So in other words, sets are things, and if you have something, another object, we could say, does this belong to the set? Is it an element of the set, or is it not an element of the set? Now that's essentially just, all it is a different way of stating the rules of elementary logic. All you're doing is saying a statement is true or false.
I see.
Or you're saying this is in the set or not in the set.
I see.
Right, so there's absolutely no difference. The rules of elementary set theory and the rules of elementary logic are exactly the same. They're just written differently. They're 2 different shadows on Plato's cave, right? But they're the exact 100% same thing. So once you know one, you know the other. But it's said in a different way. So the fundamental belief is that, you could have this collection. So everything in mathematics can be written in terms of sets. But you couldn't actually write in mathematics like that because nobody would understand what you were talking about. So even elementary results that would, in abstract algebra that you could prove in 5 lines would take 500 lines if you went to reduce it to that kind of language, right? It's like taking the program, the operating system for your Mac and trying to reduce it to assembly. It would just produce something that the machine understands, but that a human being simply couldn't understand. It wouldn't be useful. It's not in the right language.
So that actually makes sense to me now. For about, you probably told me this the 10th time, but it finally clicked. So is that's a no then? That's a not quite, or an almost?
I don't know. A no to which question?
To the question of the question about collection and whether about ordering and unifying and the logos and whether there's a one, because the Platonic question really hangs on whether there's a one or not, because if there's a one, then you can add another one, and then you can count, and then you can pull things together in order of the world.
So I would say, yeah, and from the set theory point of view, the numbers, the integers, the natural numbers are defined as sets. So the only thing you really need to know is that you can have a set, and that you can have a set with nothing in it. So if you have something with nothing in it, you have an empty set. But then you could take a set that contains the empty set, right? That's something different. Right, and you basically use this technique. And just keep taking sets containing. So in other words, 5 is the set 1, 2, 3, 4.
I think that's von Neumann's definition of ordinal numbers. Right?
Yeah. So that's exactly right. So I mean, all you need is the empty set. As long as you believe that there's a set in it. So that's collecting nothing. Then you can construct all of the integers. Once you have the natural numbers, once you have the natural numbers, you can construct the negative numbers. Then you can construct the rationals, and then you construct the reals as limit points of the rationals. So you get all of this.
Trickery.
It requires some trickery. Then you have to assume certain things about the real numbers, right? You have to. You need limits, and you start to need topology.
That really comes in.
Yeah, you have to accept the infinite. Because you have things, say like the square root of 2. The square root of 2 cannot be represented as a finite decimal, right? But there you're believing that you can add up infinitely many numbers. Now we make very rigorous definitions of this in mathematics, so mathematicians don't doubt this, right? But you still have to say that, okay, the thing that we're defining, this limit, is actually the sum, and things like that, right? So it's, we use these words like sum and size. Like we use size to indicate cardinality, really talking about cardinality, a very specific definition of cardinality. But colloquially, we say size, so people understand it, right? Which is always dangerous. We should say it just in the rigorous cardinal definition, right? But then nobody would understand what we were talking about.
I see. Okay.
Which nobody understands what mathematicians are talking about anyway, so maybe we shouldn't even trying.
That wasn't the answer I was looking for. But it's helpful. It certainly is helpful. Yeah. Can you go back to one thing you said about the set, about nothing and the set of nothing, and about that? Can you say something?
So if you have the empty set is a set that contains nothing. There's no element. There's no element A for which A is an element of the empty set.
And it would be ridiculous to say, well, what is it?
Well, it's the set of nothing.
It's the empty set. The empty set is not nothing.
Well, that's what I'm asking. Yeah.
It's a set, but it doesn't have anything in it.
I see. Okay.
That's different than nothing.
Okay.
Right, so there you have the empty set. It has no elements in it. But now if I take the set that contains the empty set, that set has one element in it. That element is the empty set.
Okay.
Right, so this is you're showing where set theory has its power. Because if set theory has its power because you're assuming next to nothing. And then you could just use this next to nothing to start building mathematics.
Yeah.
Right, so then once we have the real numbers, we have the integers, we have everything, we have all these things, then we can start developing all kinds of other things.
It's just interesting. I think I'm starting to get a pathway into how you think. And it's very different from a philosopher, because I'm concerned with, well, what is it or isn't it? You both keep saying, well, if you assume this, then you get this. As long as you assume this and you account for this.
I think that's I don't know. That's something that sometimes I just get the impression that's not appreciated. That, I mean, what we're doing is stringing things together.
Yeah.
Like there's a premise. From the premise, there's a conclusion.
Yeah.
There's never not a premise. Because you don't prove the premise.
Right.
You prove that the conclusion follows from the premise.
Right. Very cool.
Oh yes, that reminds me. The other thing I was going to say is I was reminded that like when I on in grad school, when my professor said, like, you never really prove a theorem. You just convince another mathematician that you had to.
That's interesting. I was wondering about that. Like, how do you know? I think I asked you that the other day. How do you know?
Well, that's true.
You really
Because,
prove something.
this is like saying, okay, can I go back and construct this all rigorously down to assembly language?
Yeah.
Nobody wants to see that. So your proof is, yeah, if we have to go that far, we can go that far, but look at what I did from these other results. Because it has to be intelligible. Because we're explaining mathematics to other human beings, not to machines.
Right.
When you're explaining it to machines, maybe you need that other kind of thing. And for a machine to check a theorem, you have to get farther and farther down there, which, I mean, people are trying very hard now to construct machines that will check a proof. But it would require us to write the proof in a very different way. So if you think about, say, Fermat's last theorem, the most famous theorem of the 20th century, proven by Andrew Wiles. His proof, if I wanted to understand that as a mathematician, in a very adjacent field to his, it would take me 30 years of reading to get his proof. I mean, it would really be that long for me to understand the whole proof. Now, that's written as mathematics intended for another human being. If he were to turn that proof, the whole thing, into a proof that could be verified, right? We're looking at a proof of who knows how many lines, millions upon millions upon millions, right? So what would the point of that be? Absolutely nothing, right? So at some point when you're proving, you're saying, okay, I'm assuming A, B, C, and D. I'm not going to spend every day reminding myself of why A, B, C, and D are true. I'm using them. They're my tools now. Because you can't get anywhere if you keep going back too far. You have to say, okay, I trust A, B, C, and D, right? They've been theorems for 100 years. I believe them. I know that they work. And then you can use them. Otherwise, you're not going to advance the theory at all, right? So in a proof like Fermat's last theorem, which is highly non-elementary, it uses so much other mathematics and algebraic geometry and the complex numbers and things like this, modular forms, all these other theories that it's maybe impossible to know the whole thing all at once, right? It's like if somebody was going to build a computer, you can get the smartest person in computer engineering in the world to sit there. He can't build a computer from scratch because he might not know how to make plastic, right? He might not know, right? He doesn't know how to make glass, right? But he could. So if you give him the objects, you give him the screen and the plastic casing and the everything like that, he can construct a computer. But the individual parts he may not know how to do, right? He may not know the correct way to make plastic so that it doesn't melt when you're doing things, right? It's so you're using the thoughts of other people to advance the theory. So then we can get a computer, we can get an automobile, right? The person who designs the automobile may not know how to, say, make the cloth that sits on the seat or something like that, or the more complicated things, right? I mean, most cars have a computer in it now, so he might not know how to make the computer in the car, but he knows that if I just detach this, then it can operate the system that he wants. Right, so it's the same thing in mathematics. We may not know every single thing that we're doing, but we're using results that we know. So that's the way set theory is. Everybody accepts set theory. It's explained to you once when you begin mathematics. You trust it, you believe it, you never question it again as long as you live.
That's right.
Unless you're teaching it, or you're on a podcast, right? So then you don't need to question this. It's just there. We have these tools, right? And we accept the tools we have. Because in the body of mathematics, if someone were to prove an inconsistency anywhere in the body of mathematics, the whole thing is wrong, right? So we've been doing this for over 2,000 years, and there's no inconsistency so far. So mathematicians believe that our system that we've constructed is consistent. In other words, by consistent, I mean you cannot prove a statement and its negation. Right. So we all believe that this is this consistent system. Because we think if it weren't, somebody would have figured something out by now, right? So we trust the system. Because if it's wrong, the whole thing is thrown out. Right. And also because, as we said before, the efficacy of mathematics, its use in chemistry and physics and biology, it works all the time. Let alone economics, everything else, right? I mean, things have to obey mathematics, right? It's predictive power. It's way that it sits underneath every other discipline. In the same way, a scientist, a physicist, a chemist may use mathematics without understanding any of the foundational principles of mathematics. They have a formula, they know this formula works. and they use that formula. So they're advancing the knowledge using mathematics without necessarily being able to prove mathematics, right? They may not be able to rediscover calculus on their own, but they certainly apply calculus extremely well. They may be phenomenal practitioners of calculus. They may be able to find any integral you want, and sometimes they really are. But it doesn't mean that they're really worried about the foundation. They know how to use it.
Okay, so would you say, and I imagine your answers would disagree here, on the relationship between mathematics to natural science and the utility of mathematics. It sounds like you're saying, well, there's a kind of safety check or a safety net that we have with natural science. Well, at least we know we're onto something if they can still use it, but we want to keep it still pure as this, whereas I think you might be okay with saying, whatever with that stuff, as long as we can apply it. Although I don't know. I don't. So how do you see what you do in relation, what both of you do in relation to natural science?
Well, I mean, coming from my background, what I would say is the kind of difference between, say, like a physicist and definitely an engineer, as opposed to an applied mathematician.
Yeah.
Is physicists and engineers are happy to use an approximation to get an answer.
Right.
An applied mathematician wants to use an approximation, but be able to state rigorously what is the error in making that approximation.
Oh, that's fantastic. I never understood that. That's great.
And a pure mathematician would rather die than use an approximation.
Wow.
And I think the difference between, so I'm a pure mathematician who does applied things sometimes. Jason is an applied mathematician who knows pure mathematics very well. So I would say the difference between a pure mathematician and an applied mathematician is a pure mathematician is seeking to find new theorems of mathematics, full stop. If perchance they have an application, great, use it. But I'm not really concerned about that. Even when I'm the one doing it, I'm really not concerned about that. I'm just doing it because it's something interesting. Where an applied mathematician really wants to take the mathematics that exists, and maybe he has to add to it, to construct interesting things in the world. So Jason can make a model, and he takes the already well-developed theory of differential equations, and he applies this to the model. But now he may have to prove new theorems in differential equations to make this work. So he proves new theorems, but his goal is slightly different because he wants to then make the model that says, okay, this is how your knee is working, right? Where a pure mathematician is just saying, I want new theorems for differential equation. And if somebody else can use them to help you understand the knee, great. And I'll even help you do it. Right? So, I mean, in reality, a lot of times you're doing the exact same thing. Mm-hmm. It's just that we view what we're doing very differently. Mm-hmm. Right? So, yeah, sure. You could do the mathematics and apply it somewhere. Mm-hmm. But that's not really my goal. Where it is Jason's goal to apply it. But we're doing a lot of times the exact same thing.
Yeah.
I would say that mathematics is a extremely powerful method for theorizing about the natural world. Yeah. But you have to be careful, actually. And if you can't justify that the mathematics you're using to theorize about the natural world is consistent, then it's your theorizing is questionable.
Do you think that? Oh, good. Sorry.
You may have the wrong model, and then you're predicting the wrong things. If Jason said this differential equation is modeling the knee, and it's not modeling the knee, then his predictions are out the window. So he could say this is going to work.
It's more than that. It's like if you claim that this mathematical model is a model for physical reality, that model better be consistent within mathematics in the sense that
I see.
You have to be able to prove that this differential equation has a solution.
Yeah. So you have to be right in both places.
And what happens
in the natural world and in the mathematical world, you have to be consistent in both places.
Often you can't solve these equations; they correspond to mathematical models.
Okay.
So you have to rely on some computational tool to approximate a solution, but that's not the same as the equation having a solution.
Okay. Do you think some of these problems, and this is just a question I have to do with reality, physical reality, resisting the intelligible constructs of mathematics, or is it something? Or is it just an error in the computation about the mathematics? Is another way of what you were just saying. So, in other words, what's the relationship? So,
It's not easy to model. Well,
how much of the models correspond to the
I
reality?
mean, there's this trade-off between you can, if your goal is to make a prediction about some system for which you have a ton of data, you can do that perfectly. But the problem with that is that you've essentially just fit the model to the data.
Mm-hmm.
You haven't actually modeled nature.
That's interesting.
Right? And that's why people don't like complicated models. But outside of like reducing things to basic physics, it's very difficult to come up with simple models that also do a good job of predicting the data.
Oh, very interesting.
So, and that's where the math comes in, because you need to make sure that, well, your model's not too complicated so that you're not just overfitting to the data. And your equation is not so simple that it tells you nothing, and that your model is mathematically consistent.
So how mathematizable is nature? Because this is a big question in philosophy of science. There's some guy, by the way, Max Tegmark, who thinks if you just drill down, everything is just numbers. Like, I forget what that's called, but
I mean, there's
That's Descartes' dream.
yeah, that you could just sit at your desk and do the whole thing.
And Descartes said that everything is mathematizable.
Yeah.
I mean, there's a book about that.
Mm-hmm.
I mean, it's difficult for sure.
What do you think?
Some things resist math. Some things currently resist being mathematized.
Yeah.
Like, for example, a mathematical model for the human brain.
Yeah, that's interesting.
That generally means I think we just don't understand it.
Yeah. Yeah.
So maybe in 10,000 years we might have a nice model, but maybe not.
And if we modeled it, could we totally predict it? The mind or the brain?
Well, I don't know. I mean, you can, like, even within physical models, you can.
We could model a pair of dice, but we can't predict the pair of
exactly.
dice.
So uncertainty is inherent.
I see. Yeah, that makes sense.
I mean, if we could predict a pair of dice, we could just end this podcast and head out to Atlantic City and try to, right? But I mean, so we know why the dice roll the way they do, right? That's not difficult mathematics. However, even the slightest little change in the way the person who's initiating the roll of the dice, in the way that they do this, could change the roll of the dice, right? And there's ways to cheat that, as we all know. You can have a weighted dice, things like this, right? But so there's always that. So this goes back all to the quantum mechanics, right? Where Einstein didn't like this. He didn't want God to play dice with the world, but it seems God does play dice with the world.
Well, the reason I ask this is because these kind of questions come up in philosophy when it comes to like what's the nature of the mind and intelligence, and there are obviously two sides of this. Some think that it's impossible to map it precisely because there has to be an element of choice or freedom involved, and that's unpredictable. Or this other idea, well, if we knew all the variables, we'd be able to.
You have to be careful about what is it you're trying to predict. Like quantum mechanics is a good example. You can't predict with exact certainty simultaneously the position and momentum of a particle. But that doesn't mean that quantum mechanics doesn't make predictions about the world. Mm-hmm. As a theory.
Right.
And so, I mean, if your goal is to like plug some numbers into an equation and figure out, what Duane's going to eat for breakfast tomorrow morning, that's different than like being able to make rigorous statements about how human physiology works.
Sure, yeah.
And there becomes a question of the complexity.
Mm-hmm.
In other words, if you had to answer 2 to the n questions to predict, and that n goes to 100 or 1,000 or 1,000,000,
right?
All of a sudden, it doesn't matter that we know the questions that you'd need to answer to predict.
Right.
It's too many for us to actually predict.
Right.
Right. So then you were in a situation that's just too many.
But don't you still think that's qualitatively different than saying there's still some element that is fundamentally impossible to predict, or there's still, that there's something about consciousness? This is the questions of consciousness.
I would say that. It seems that there is something like that's non-predictive in consciousness, right? But I think the physical aspects of consciousness we understand so little, it's very hard to say anything. And even if we were certain of one way or the other, would it really change the way that we say live our lives or our fundamental beliefs? I don't think so, right? It's just it's almost like finding it's like not set theory. Okay, we have it once, and then we go back to living our lives and doing mathematics, right? I mean, okay, so I know that there's this predictive aspect in my mind. does it really affect what I'm going to have for breakfast tomorrow? No, because I'm going to still think about what I'm going to have for breakfast. Does it affect your thinking? Because we're still thinking. We're actively engaged in thinking.
I'd like to hack it if we could predict it, and say,
Turn yourself into a mathematician.
make myself like eating healthy and stuff like that. So, yeah.
All right, so let me ask another question here. In Plato's Academy, above the door of the academy, it had the famous phrase, let no one destitute of mathematics enter through these portals. So what do you see as the role of mathematics in the education of people, especially in the education of people within our Catholic Jesuit tradition?
You asking me?
Anybody?
Oh, go ahead.
Obviously, I would argue that the more math you know, the better you are, the better off you are. I would say that it's extremely empowering. An education in itself is extremely empowering. I think an education that includes mathematical training is doubled or multiplied by some factor that increases.
Is mathematics like a sine qua non, a necessary condition before you study philosophy?
So the Jesuits thought so, in the sense that they thought logic, at least the study of logic, was a necessary, propedeutic or whatever to preparing for study of metaphysics and things like that. You had to take a logic class, and that was in the Ratio Studiorum. So I would think the same thing you're talking about. The benefits from studying rigorous math is the same as, I think, studying rigorous logic. You learn how to think, and you learn the parameters of thinking, and Plato would say, and this is mythologized, but the more time he says philosophy is the art of dying and being dead. What does that mean? Every time you do a little math, you separate the soul from the body. You're in that other world. You're flying. Now, I think that world is real, and so I think the longer you spend up there, you called it empowering. I would say you're breathing the clean air up there of the Platonic world. Yeah,
we talk about a liberal education, and that's where it comes from. Being
yes.
liberated.
Yes, exactly.
Exactly from Plato, being liberated.
I'd say mathematics is metaphysics, and I think the more we go metaphysica, the better. The more we stay in the physica, bummer.
So this is a bad question for us because we want students to take our classes so they'll run.
Well,
right? So in some sense we're dependent because the deeper you get into mathematics, the fewer students that are capable or have the background to do it. Right? So it's very hard to run a high-level mathematics class. You have to, because say you really want to take a good abstract algebra class. Well, you need a lot of prereqs to do that, even though we say all you need is this, but each prereq has a prereq. Right? You need a certain level of mathematical sophistication to understand it.
Yeah. Well, okay. I think the better way to sell this is not that it's simply a skill. I don't think mathematics is just simply a skill. I think it is liberating because I think it is metaphysical, and I think it is you're dealing with truth, and I think mathematical truths are true, and I think they're real, and I think, so it is a skill that you can apply, and it's beneficial one, the wrong one to teach you how to think and stuff, but I think there's something for this, studying math and logic and, or metaphysics, whatever, like what's the point of, thinking about being qua being, these kind of things. I think there's a liberation, because all human beings desire to know.
In practical terms, which I almost never care about practical terms, I think the difficulty in that is, by the time you get to where mathematics is liberating, you might have already gotten like 2 master's degrees and started your PhD. Like if you asked a student in the 3rd semester of calculus whether this was liberating their soul, they would say, no, this was torturing me and preventing me from going out on Friday nights.
Yeah.
Right? It takes a lot. If you hear a piece of music, you immediately appreciate the beauty of that music, right? You sit down and you listen to something just wonderful, some Mozart or Bach or Beethoven, and you say, wow, that really moves me, right? But you could look at Euler's equation, right? And even if you understand it, you may not see the beauty. But somebody who really, really understands it, and I mean understands it on an elementary level, somebody who really understands it on a deep level sees that and just sees the beauty. By the time you get an appreciation for the beauty, you've had to put a lot into it.
Well, this is why Plato and Aristotle, particularly Aristotle in Nicomachean Ethics, says the higher pleasures require more and more discipline until as you climb up the ladder for the most exquisite pleasures. They're the most difficult to attain. It's very difficult to understand.
High up there.
Well, yeah, I mean, the pleasure, just looking at Jason's face when he was talking about some of the abstractions, you said there's such a power, there. And I think that's what the Greeks thought, that, they weren't for everybody, but that's why I think liberal education is trying to include as many people as possible in these higher pleasures. That's because
I definitely think mathematics is for everybody. I just don't think that it's sold. It's definitely not sold that way. I mean, there's a lot of people that are told that mathematics is not for you, and I just don't think that's true. But it is, like, you have to find a balance between, because some people do need, I mean, it is useful. Some people do need to know mathematics to use it, but not everyone does, and so they have no motivation to study it. And I think it's because, I don't know, we don't sell it well enough.
Well, I'll say this, Plato famously gave a lecture on the good, his best lecture, Aristotle tells us, and it was all mathematics. So the highest lecture that he was giving, it was on, and nobody understood it. They were like, what he was talking about was all numbers and, abstractions and stuff. But philosophers have a great respect for mathematics, at least philosophers, metaphysicians, realist philosophers, or,
So Jason, go ahead.
I see a lot of people get excited about ideas that are really actually more complicated and harder to understand than math. It's just that it's not hidden in the same way. Or I guess maybe shaded, there's a word I'm looking for, but cloaked in the same way? I don't
Cloaked,
know.
I think, is the good word.
And I wish more people could get exposed to ideas that are interesting.
All right, so which result in mathematics would you see as being, say, highly beautiful? That you would say, look at this is an aesthetic quality in mathematics.
Yeah. I don't. There's not a result, but there's like
Or a theory.
proofs or derivations that I think are interesting. Like, just the simple proof of the infinitude of the prime numbers is like, it's very interesting, I think. I mean,
And that goes all the way back to Euclid,
Yeah, find it.
3rd century BC.
Yeah, I mean, I think if you could show that to someone who's really young, I think they would find that very attractive. It's not, yeah. I mean, there's a lot of things like that.
So which courses did you take that really made you feel like, oh, this is the thing I want to study? Which one really shocked your mind?
Yeah, there were a lot. I mean, the first one that made me become a math major, moving away from physics to become a math major, was dynamical systems, because I realized that the questions that the problems that you're trying to solve in physics can be put into this one rigorous but also broader framework. I really liked linear algebra a lot, and still do to this day. I'm teaching it for the first time ever, actually next semester. But and all the sort of generalizations of linear algebra I find really attractive. So probably those two courses.
I find, when I think of linear algebra, I think of it as geometry, which it
absolutely.
is,
Yeah.
because I've done a lot of finite geometry, and I view all the results in that way.
Yeah.
But I think people could know linear algebra pretty well and not understand that it's geometry at all. In other words, they could use linear algebra really well.
I think that's part of the power of it, in fact, is that you are effectively doing geometry by just manipulating some symbols.
Yeah.
And that is underappreciated for sure, especially when you take it as a student for the first time. But that's also what makes it really powerful, is that things that are geometric and difficult to do by hand, and certainly in your mind, can be done easily by just following a few simple logical.
I've always felt that's a hole in the education of students generally, is that we don't give them enough linear algebra. Because and not just at our school, at every school. Because linear algebra can be applied absolutely everywhere.
Right.
Everywhere. There's no place where linear algebra doesn't find application both inside and outside of mathematics.
Yeah.
But people want to get to the more exciting parts of mathematics. So they just want to forget about linear algebra, and I'll teach you the linear algebra you need later on.
Right.
But a really good foundation in linear algebra would then help you in geometry, would help you in analysis, would help you in abstract algebra, helps you in everything.
For sure.
In my own discipline, it's all linear algebra based. And very complicated. I mean, much different than the way we teach it to undergraduates. Say we're looking at modules instead of vector spaces, things like this, so that it becomes much more complicated. But the power of it is just enormous.
Right.
It has so many applications, so much use that I think it's worth studying much more than we give it to students.
Yeah. I've been learning more statistics lately, and linear algebra is fundamental to a lot of that as well. But one thing I was going to say is, one thing I wish I would have, one, been exposed to more, but two, appreciated, is the power of geometrical thinking and reasoning to guide your intuition and proving theorems and also deciding what to prove.
That's interesting because the one thing I learned from my advisor, the thing that he told me the most, was that your intuition should always be geometric and your reasoning should always be algebraic.
Yeah.
And when I tell students, I tell them that's the one thing you should think of, because your intuition as a human being is geometric.
Yeah.
It's easy to explain things geometrically to people, right? If you explain something, if I explain to you, okay, here's a sphere, it looks like a beach ball, you really have that image in your head, right? So if I say, okay, now I have a plane that's going to slice the beach ball, what do you get? You can get that circle when you slice it, or you can maybe do it at a point or something like this. But if I say to you, here's this equation, x minus h squared plus y minus k squared plus z minus l squared is r squared, and you say, okay, now I'm going to intersect it with ax plus by plus cz equals d.
Right.
What do you get? That's not intuitive in any way, shape, or form, right? You have no intuition. But if you actually want to find what you're doing, that's the way to do it. You need to use those equations.
Yeah.
But if your geometric intuition is showing you what you're going to get, then you understand that much earlier, right? You understand what's going on, right? And I think that applies in every branch of mathematics, but people rarely know how to do that. I'd say undergraduates rarely know how to do that.
Definitely.
It takes a long time to do that.
The thing that strikes me as odd about that is I would think that's what you would be the best at when you're young. And so, is that
you beat it out of
trained
people.
out, yeah.
It's trained out of people, and then you have to train it back. I think because if you took a 7-year-old, they already have that,
Right.
and then by learning mathematics the way we do, by just learning rules and computation, they've lost that.
Right.
Over the years. But I don't know how you could teach it without losing it. If you could figure out a way to teach young people and not let them lose that, it would be fantastic. So let me ask one last question, given the nature of our podcast. How do you see mathematics as fitting into the Catholic intellectual tradition?
You mean other than what I said? Because I'll just repeat what I said. I mean,
I mean, do you see this as an important part of the Catholic intellectual tradition?
Yeah, absolutely. I mean, certainly the Jesuit Catholic intellectual tradition, but I think the Jesuit is very representative of that. But I mean, because I think mathematics isn't just a skill, and I think mathematical truth I think the study and pursuit of truth in and of itself is exactly what the Catholic intellectual tradition is. I mean, this is why the Greeks were obsessed with mathematics, and why Catholicism is really the baptism and marriage of Greek philosophy and Hebraic thinking. And so the pursuit of metaphysical, abstract knowledge in and of itself is absolutely essential. I wish they'd require more math classes and logic classes and things like that. I really do. I'm say that. I mean that, because I think there's only benefit of that. And I think there's something about sitting down and working at something like that there's the payoff of that may not be obvious, but if people can learn to like that kind of abstractions, that we do or that you do, in philosophy and these kind of things. But yeah, absolutely.
So do you think having a Catholic philosophical position would force a view of Platonism on you for mathematics? So you think you could have do you think you could be steeped in Augustine and Aquinas, for example, and still think mathematics is something not eternal?
So that's a different question that you asked me earlier. You asked me about theism, or the theism necessitated.
So this is much different, because I think you could be a theist and maybe not be a Platonist if you have a different notion of God. But in the Catholic notion of God, you have an omniscient God.
Yeah. I think
a God who interacts with creation, right?
Certainly, in both the East and the West, the basic metaphysical backbone of Catholicism is Platonism, not Aristotelianism. It's a kind of Platonism, because Augustine is really, Thomas Aquinas is really the go-to, but he uses Aristotle, but a Platonized version of Aristotle that he gets through Augustine. So, no, I think absolutely not just with regard to mathematical objects, but metaphysical objects like the good and the true and the beautiful, things like that. And they're all reflective of God's nature. But Platonism is really the standard metaphysics of.
Certainly, the Greek Church Fathers, most of the Church Fathers, they were steeped in Greek mathematics and this view of mathematics as a Platonic entity.
Yep. Oh yeah. And Augustine has a proof for God in the second chapter of I think it's the second chapter of On Free Choice in the Will, that uses mathematics, the nature of mathematics. It's something like the ontological status of mathematics. How did that points to God.
Gödel too had a proof of mathematics that he never published.
Yeah.
He didn't even show it to anybody. It was just on a sheet of paper in his office, which Gödel had. I mean, that doesn't really mean Gödel didn't want to share it with people, but he had theorems and and writings on his desk that he never showed anybody.
Yeah.
He was just very secretive about everything he was doing.
Yeah.
Jason, you have a comment?
Yeah, well, I just will say that I think if you value education and learning, especially with the idea of promoting that as a lifelong endeavor, that mathematics should be a part of that, because I think that's one of the best ways to empower someone to learn and educate themselves. You can't learn. I mean, you can't learn about the physical world without math. So if you want to understand your place in the world, I think math is a requirement.
Well, you're also a musician, so you need mathematics to study music.
Yeah, that's definitely true. Yeah,
I mean, even a musician who doesn't understand mathematics at all is really understanding it. They just don't know what they're getting from mathematics.
And there's so many parallels between the two. I mean, I could be biased because I like both math and music, but I mean, the more that I immerse myself in each one, the more similarities I see between them.
I would agree with that.
Yeah.
So do you have a concluding statement here? We'll give you each a chance to give one concluding statement.
So we started talking about what the nature of mathematics was, and I think there are really two positions you can take, and I just think Platonism is you could say it's either created or discovered, but to say it's created, you'd have to say you still have the problem of the unreasonable applicability of mathematics and why it works, and I guess you'd have to look, so there are two ways of looking at this. Either we're looking at the math, we're doing the math, and that's sort of up here, and some of it applies to the physical world and some of it doesn't, but then there's math in it itself, which is a reflection of the universal mind, God, whatever. Or you can say somehow that mathematics is this language that we abstract from physical reality that we use as a tool to understand, and then we can just kind of play with it ourselves, and that doesn't seem to explain, though, why the way in which actual mathematical science works versus in the way physics works. It's not as though we're as far as I understand, mathematics seems to operate here and independently of the natural sciences, and then crisscrosses and things like this. And so I think all the evidence points to Platonism, or now Platonism with an asterisk. What does that mean? I don't know how that works out. But by Platonism, I simply mean that mathematics has some ontological status, some objective, mind-independent status. Yeah.
I don't mind if everything points to Plato.
Good. Yeah.
Well, I think it's interesting that, I mean, math from its earliest inception, I think, grew along investigations into the natural world, and mathematics continues to this day to be inspired by physics, and there's it goes in the other direction too. But finally, what I really find interesting about mathematics in and of itself is just surprising connections, continuously seeing surprising connections between things that you don't think that there's no obvious reason from the start to think would be connected.
It's interesting, my advisor used to say, to the chagrin of many people in the room, that the point of applied mathematics was to enrich pure mathematics, right? So I would definitely not go that far, but it's making your point that when we look out into the natural world, into the sciences, into the social sciences, everything, it gives us a lot of interesting things to think about. My own discipline had its origins in electrical engineering, but the things I do have nothing to do with electrical engineering.
Right.
It was we saw, they said, here's this question we have, can you answer it? And then we said, wow, this is an interesting question. And then we looked at it for its own sake rather than for the application.
Right.
But still, within algebraic coding theory, we have a healthy to and fro from the electrical engineers. They still provide us questions, we provide them answers, they provide excellent ideas for us, right? So it's a good conversation. I think mathematics thrives when you have that conversation with the other disciplines, because they're encountering things that they cannot solve, and then they hand them to us, and maybe we can't solve them either, but it gives us something to think about. It shows us new ideas.
Right.
Oh, great.
All right, so thank you very much for joining us here today for
Thanks,
this 2-hour podcast. Thank you very much.